Okay, we're gonna spend some time here kind of defining or figuring out our feed fractions. What you're gonna need to do from Blackboard is print out two items. One is our blank NDF graph, and then the other is our NDF remaining table. So you can take that information. So we're gonna be we're gonna be focusing on the in vivo. But this is pretty similar for in vitro as well. And what we're going to try to do here is think of a single feed particle as we move through. So we're going to take a graph here of the percent NDF remaining. And we're going to think about in vivo. So if we were able to leave the NDF particle in the rumen up to 240 hours, this is what would happen to it. So you're going to have this level spot here. The feed goes into the rumen. It needs to be saturated. It needs to have microbes on it, and then they need to start to work. That saturation, attachment, and then digestion, fermentation takes a little while. So we're looking at usually 2 to 3 hours. We call that the lag period. So for the first part here, we're still at 100. Once the microbes are attached and they begin to work, they begin to take apart the NDF, and we start to lose NDF. And we're going to go down through this shape, more or less. We're going to have, if you smooth this out, reality of curve. But if we take the measurements that we can get from a lab, a 12-hour, 24, 120, and 240 hours, and plot those out, we can get a shape of a curve looks like this. So you're going to notice that the NDF, some of it's going to disappear very quickly over the first 24 hours, and then what was left is not going to disappear nearly as fast. So we're going to have some what we're going to call fast fiber being digested or fermented here, and then we get the slow fiber here, and we get to a point where that's all we can do. So if we start to divide this out and quantify or put names on these relationships. So we're going to start with what we're going to call here is our bottom limit. This is about as much as potentially digestible in the thing. So we've got somewhere around 15% here, and what would measure as NDF will never be available to the animal. So we're going to call that indigestible, infermentable. The microbes cannot tear it apart, even if you gave them 10 days to do it, they still could not destroy it. That divides our NDF into indigestible. So that 15% in this example is completely indigestible. And then we have the other 85% is potentially digestible, potentially fermentable by the bacteria. And you can see that depending on how long our feed particle stays, will depend on how much actually is digested, how much is degraded, how much is taken apart by the microbes. So we're going to get down, the first 60% is going to go in the first 12 hours, and then things are going to get a lot slower. We get to 124, we're looking at somewhere around 30% on this graph. So you still got some stuff that is potentially digestible, but if that feed particle only stays around for 120 hours, the 30%, this 15% will not be used, fermented, digested, not become part of microbes, not become VFAs. More often than not, we're looking at something in here is the residence time, somewhere from 20 hours to 40, 50 hours. So in this case, somewhere around 60% of the NDF is digested, and then 40% is undigested. 25% would be potentially digestible, but 15% is not. So we think about how our NDF is divided up. We've got digested NDF or digestible NDF. UNDF is the NDF that can't be digested. So this you can think of as potentially. This is the stuff that absolutely cannot, and depending on where you measure that. Usually that's 10 days in rumen fluid. Some people will use 5 days. You add those two together, they always have to add up to the total NDF. So all the NDF that's there has got to be in one of these two categories. If we think about this in vivo, we've got a total NDF going in. Some's going to be digested, some is not, and be passed through the animal. Our job is to get as much of this as we can, as fast as we can, to help our animal move forward. So again, looking at what's there, undigested or digestible NDF, undigestible NDF down here. DNDF from here to here, and then UNDF is what's under that line. With our DNDF, we've got different pools, and normally we'll divide that into 3 different pools. We have a very fast pool, so we have a very steep slope here, so we have a very high digestibility rate per hour. Then we have our B2 pool that is a little bit slower when it comes to digestion. They're all being worked on at the same time, but this will disappear much faster than this and much faster than this. So very slow rate of digestion. The shape of the curve shows what proportion is in each of these 3 pools. B1, B2, B3. The faster this drops, the more B1 we have. The slower this drops, the more B3, the more B2 we have. So we take this apart by what's known as curve peeling. You can see that if you sort of did the average or aggregated these 3, they would sort of generate the shape that we see there. So fast fiber goes first, our B2 or slower fiber goes, and then our slowest fiber disappears last. So depending on how long things stay in the rumen, somewhere in here, we may lose all of our B1, a proportion of our B2, and only maybe a little bit of our B3. And that's what becomes the VFAs, that becomes the microbial bodies that the cow has to make her living off of. So let's do the graphing here. So you need your blank form, and you need that table with the values for the conventional corn and the BMR corn. We have these are actual measurements taken off a feed analysis form. We had some conventional corn silage here a couple years ago and a BMR kind of the same year. And so you can kind of compare them head to head. So if you're thinking about the percent remaining in vitro, we've got 100% at the start of the lab analysis, and then how much is remaining after 12 hours, how much is remaining after 30 hours, 120 and 240. So this is pretty much inert. This is mostly from here to here is certainly all that B3 fraction. Up here, you're looking at your B1 fraction between those two. So if you take those numbers and graph them on your graph paper, you're going to get a thing that looks like, there's your graph paper, which you need to print out. And it'll look something like this. So we'll do the conventional is the green line coming down. That's the higher of the two. The BMR is the blue line. So we know that BMR has less lignin in it. It has a tendency not to be as strong a plant. One of the problems with BMR is it can't grow as tall, so you get a little bit of a yield drag sometimes. And we also will get things falling over faster because we don't have as much lignin. We have a defect, a mutant gene where the lignin is never fully formed. All the components are there, but you don't get the rigidity that's associated with the conventional. So if we look at the shape of the curves here, we're going to see some differences that we need to talk about. So it doesn't look like much, but it makes a huge difference in the rumen. First thing we have to talk about is what's the undigestible, the UNDF. So we can move this line up and down. We've got 18, about a fifth of the conventional is undigestible versus 10 of the BMR is undigestible. So that's a pretty big range there. We move this line up and down depending on which one we're doing. So we've got more undigestible in the conventional, 8 points different than the BMR. So depending on where that line is, we can move this line up and down to accommodate the two different hybrids. And then we start to think about the slopes. With the BMR, we have more in that B1 fraction, more in the B2 fraction. So you're going to get a more steeper line here. This line here, the blue, is much steeper, not much steeper, but is steeper than this. And it's in that rate that we get the gains associated with BMR. We'll get more intake associated with a BMR. The animals are going to consume more. The NDF digestibility in the rumen may not change all that much, but we get to that level, that digestible NDF, a lot faster with the BMR, so we get grease turnover, increased removal from the rumen, so we have more opportunity to eat more. Is we have more in this B1 fraction because of less lignin. We have more available NDF quicker. The bugs turn it into protein faster, excuse me, into VFA faster. So we're going to get better turnover of that BMR. And in that is the advantage of having BMR. We may not get necessarily more NDF total consume per day, but what we do disappears faster and becomes more beneficial to the cow with VFA and the microbial